Hello everyone. First, I would like to thank the organizers for giving me the opportunity to present our work in this conference. I work at the National Hellenic Research Foundation at the Theoretical and Physical Chemistry Institute as a senior researcher. The experimental part of this work was performed by Aggeliki Sklapani, an MSc student of my group. Today I will discuss our findings in hemoglobin-based nanogels. Some word on our current research on nanobiomaterials. We mainly work with protein polysaccharide nanoparticles, which is the topic today, hydrogels for bioapplications, biopolymer modified interfaces and complex fluids of biopolymers. Um, Protein nanostructures are biocompatible, biodegradable, metabolizable, and non-toxic. They are attractive, therefore, for the delivery of drugs, nucleic acids, growth factors, and nutrients. They are used in bioimaging applications and also as virus-like particle vaccine platforms. There are several methods to make nanoparticles or nanogels from proteins. We mainly use complexation with polyelectrolytes, or in particular polysaccharides, but there are also other methods as desolvation, electrospraying, emulsion, solvent evaporation, and salt precipitation. Some examples from the literature. Human serum albumin can be shown here to create nanospheres which may entrap resveratrol, an anti-tumor drug, and also be conjugated on the outside by folic acid in order to target liver tumor cells for directed drug delivery. Bovine serum albumin in combination with green tea polyphenol nanospheres can create nanoparticles of size around 200 nanometers to carry doxorubicin. These structures were also responsive in their release on glutathione and enzymes. Uh, Oil in water emulsions can be stabilized by the pickering kind of emulsion using the surfactant properties of alpha-lactalbumin. As well, here curcumin could be delivered and its bioavailability was greatly enhanced as it is a hydrophobic substance that cannot be easily transferred in water media. In food science, we can see that we can avoid adding fat in yogurts in order to deliver lipophilic compounds as vitamin D. They can be entrapped in recombinant casein micelles in protein micelles that can be reassembled and contain this vitamin and increase its uptake by cells, and at the same time it's to protect it from the gastric environment. The commercially available protein nanoparticles of albunex and abraxane are based in human serum albumin. They have the paclitaxel drug hydrophobically bound on their surface, and they can also be conjugated by antibodies for directed chemotherapy. Polysaccharides are another kind of biopolymers. They are biocompatible, non-toxic, biodegradable, and safe as proteins. They are used, of course, in food science and in medical science, and in particular in tissue engineering and wound healing, as they are polymers, that they are very hydrophilic, and as we say, biologically compatible. In food science, we can see that they can be used also as stabilizers. Here we have a complexation, a combination of alginate and an ionic polysaccharide with ketosane and cationic polysaccharide to stabilize creams. Ketosane here, the cationic polysaccharide we mentioned before can be conjugated, can be modified by side chains of hydrophobic units, and this is a self-assembling polymer, of course, with a hydrophobic core and a shell of hydrophilic polysaccharide, which can entrap hydrophobic drugs and deliver it in aqueous media. In wound healing, we can see a combination of two oppositely charged polysaccharides can create networks that can be used as scaffolds to create new cells and heal scars and wounds. We think of polysaccharide and proteins as polyelectrolytes. In the first case, we have charged polysaccharides of natural origin, and in the other case, complex biological polyelectrolytes. We have a globular shape in general. They have a complex surface charge distribution, which is also pH dependent. As we can see here, a protein can interact attractively with a polyelectrolyte even though the protein has also charges of the same size with the polyelectrolyte. It only needs to have some surface charge patch which is oppositely charged to the polyelectrolyte. We can think of new nanobiomaterials, nanostructures, by self-assembly between these two components, mainly by electrostatic interactions. We can think of nanoparticles, of multi-layers, alternating layers of polysaccharides and proteins, and hydrogels or nanogels, networks of these two, the one acting as a cross-linker for the other, and hydrogels or nanogels depending on the length scale we decide to prepare them. In more details about the surface characteristics of a protein, we can see that we have the charge patch, positive and negative amino acids and neutral amino acids, which can change, which can be signed with charge on R charge depending on the pH. This creates the electrostatic surface potential, and also the amino acids can be either polar or non-polar or intermediate, and this creates a hydrophobicity patch. This gives the opportunity with the proteins to interact with the environment by electrostatic and hydrophobic or hydrophilic interactions, and gives the multifunctionality to the proteins. This multifunctionality is what we use in the nanobiomaterials structures. To develop nanogels or nanoparticles between the two components, therefore, we can use biocompatible and eco-friendly methods because we don't use any chemical reaction or organic solvents. The proteins will be building blocks but also introduce their multifunctionality. We expect stimuli responsiveness to pH or temperature, and also to be able to load bioactive substances. The first principle is here. We can see an example from BSA where we have a pH below its isoelectric points. The two are oppositely charged and they should create a complex, an aggregate containing both of the two components. Another property comes from the protein where we can see that if we increase the temperature above a certain temperature, we can have a change from alpha helix to beta sheet, an exposure of hydrophobic domains, which then upon decrease of temperature back to room temperature will create interprotein, new interprotein bonds that lead to aggregation. Of course, these aggregates are not easily controllable and they have size distributions from nanometers to micrometers without any possible control. Combining these two properties, we managed to make well-defined nanogels or nanoparticles. As we can see here, we use complexation at acidic pH in order to have well-defined size distribution, well-defined nanogels, nanoparticles or complexes. We can use these terms interchangeably. We can stabilize this by thermal treatment, which means that when we increase the pH to a value where the two components are of the same sign of charge, they don't disassemble, but they can only swell without losing their integrity. This happens because the hydrophobic bonds between the proteins after the thermal treatment happen only between proteins that they are inside well-defined complexes and not randomly. In this work we present today, we have hemoglobin, a protein with molar mass of about 65,000. It is in the tetramer of two alpha and beta subunit pairs. It carries oxygen from the lungs to the tissues. This is its main property. Its hem group, its main function, its hem group has hydrophobic regions that makes this protein promising as a nanocarrier for hydrophobic bioactive substances, and indeed we have seen nanoparticles of pegylated hemoglobin to be used as carriers for paclitaxel in the literature, and also acid denaturation self-assembled hemoglobin was used as curcumin containing nanoparticles. Chondroitin sulfate, on the other hand, is an anionic polysaccharide. It occurs naturally in the body. It is an extracellular polysaccharide, important for cartilage, also very widely used in osteoarthritis. It interacts specifically with growth factors, receptors, and guidance molecules. This is our protocol, the established protocol we have used in several other systems. We have acidic pH to create the complexes. Then we perform the thermal treatment, and we have the nanogels, the nano networks between the protein and the polysaccharide, and we can also add drugs or nutrients to create loaded nanogels. The optimal conditions that we found was this concentration for hemoglobin and about 0.1 milligrams per ml, a mass ratio between the two components in a range where there is roughly balance between the charges of the two, and the thermal treatment protocol was at 60 Celsius for 2 hours at the acidic pH. As we can see here, the overall charge of the hemoglobin as a function of pH drops, of course, because of the weak character of their amino acid dissociation. We have a high charge at 54 for pH 4, but at pH 7 we have a very low charge, almost zero. As we can see on the detailed picture of the surface, at pH 7 we have both positive and negative charges, and mainly we have large positive surface patches and randomly distributed negative charges. With static light scattering, we show that we have increase of molar mass as we increase the mass ratio between the two components. Actually, we keep the protein concentration constant, and we increase the concentration of the polysaccharide. With dynamic light scattering, we show that we have monomodal, well-defined size distributions with a hydrodynamic radius that increases gradually up to hundreds of nanometers as we increase the mass ratio between the two. Therefore, we have a tunable molar mass and size and well-defined monodispersed complexes. If we increase the pH in these complexes without thermal treatment, we see disintegration near the isoelectric point, which is at pH pI around 7. This is what would happen in physiological conditions. We observe that by static light scattering, where we have a drop in the molar mass, but also we have more importantly, we have a distraction of the of the size distribution to single proteins or polysaccharides, and also to very large loose aggregates. If we perform thermal treatment, we create stable nanogels. Upon thermal treatment, the size distribution of the complexes remains monomodal. Their mass increases significantly in magnitude for low mass ratio and weakly for high mass ratio. Radius of gyration and hydrodynamic ratio does not show clear systematic change. The mass enhancement or by the application of the thermal protocol may be connected to the increase of the hydrophobic interactions between the unfolded protein globules. The electrostatic complexes formed at acidic conditions keep their integrity at neutral pH, where the electrostatic attraction between the two is greatly compromised. And finally, the thermally treated complexes can be regarded as stable nanogels. We also confirmed the size that we show in dynamic light scattering by transmission electron microscopy. Here we also saw some aggregates, but I believe this occurred only in the transmission electron microscopy because of the non-controlled drying on the grids of the TEM. We don't have this kind of aggregates in the dynamic light scattering, where it is a natural environment of the nanogels. And also we can see that they had, this is the important finding, they had almost a spherical shape. And the surface potential of the nanogels is measured by the Dista potential, which decreases marginally at the pH 4 for both untreated and thermally treated nanogels. This value at 20 millivolts is attributed to the dominance of positive amino acids of the protein on the outer surface of the complexes. At pH 7, the zeta potential changes to strongly negative, minus 40 millivolts, and it could originate from the negative patches of the protein and the segments of the polysaccharide on the nanogel water interface. The protein conformation inside the nanogels was measured by Fourier transform infrared spectroscopy at the attenuated total reflection geometry in the amide band between 17 and 1600 wave numbers. We saw non-significant changes in the secondary structure, as we see that from the deconvolution of the peak by a summation of Gaussian functions. We can see, for example, alpha helix remained at about 50%, either by thermal treatment or complexation, or by increasing the pH. And at the same time, beta sheet remained constant at about 18%. The binding of nutrients or drugs, here we have a model substances that they can be used either as nutrients or drugs, curcumin and beta carotene. As we can see, the fluorescence from the tryptophan amino acid of the protein drops systematically by adding curcumin, which means that curcumin binds on the protein. The reduced fluorescence intensity at maximum shows linear dependence for curcumin and exponential dependence for beta carotene, which means that in the second case we have stronger interaction. We extracted from these plots the characteristic binding constants, which are what is expected for the pure protein in solution, which means that these nanogels inherit the binding properties of the protein, and therefore this opens the way for systematic experiments on the release kinetics of bioactive substances from the nanogels in aqueous media. These nanogels can be used as nanocarriers of these components, or even other components as well. The thermally stabilized nanogels, either loaded or non-loaded with substances, were stable upon high amounts of salt, even higher than physiological conditions. We can see that we have colloidal stability in salt solutions. In the case of RH, of the hydrodynamic radius at pH 4 on the graph C, we see that there is some secondary aggregation of the nanogels due possibly to the decrease of the electrostatic interactions between the two. Finally, to conclude, we presented the eco-friendly methods with no chemical reactions or toxic solvent or components, and we had stable multifunctional nanogels by electrostatic polysaccharide protein complexation and subsequent thermal treatment. There was a tunable size and molar mass. There was colloidal stability up to high ionic strength. They had potential for nanocarriers of nutracutical compounds. and they are promising for applications in food technology and drug delivery. Finally, the developed protocols and experimental methods can be applied on other protein-based biomaterials. I would like to thank our collaborators in this line of research, which includes many other combinations of protein and polysaccharides, and the IKIDA program for exchange between the group of Professor Christine Papadakis in the Technical University of Munich and our group. And finally, you for your attention, and I will be very glad to communicate for any questions on these subjects. Thank you very much.